Hello everyone, my name is Shariat Tanvir. I'm delighted to present an analysis of offshore and onshore wind turbines, a critical topic in renewable energy technology. Wind energy is a key driver of the global transition towards sustainable power, and comparing offshore and onshore systems helps us appreciate the roles in meeting diverse energy needs. This presentation will explore the turbine design, environmental impacts, regulation, and case studies. I will also analyze voltage, current, and power comparison, showcasing their operational efficiency. Let's begin by understanding the design of wind turbines. Offshore turbines are much larger, with rotor diameters up to 220 meters. It can produce over 10 megawatt. On the other hand, onshore turbines are compact with capacities of 1.5 to 5 megawatts and rotor diameter under 150 meters, optimized for the cost and logistical feasibility. Environmental considerations are crucial in wind turbine deployment. Offshore turbines face challenges like seabed disturbance and noise affecting marine species. On the other hand, onshore turbines encounter land use conflict, wildlife disruptions, and community opposition due to noise and aesthetics. Let's talk about policies and regulation. This slide focuses on regulatory framework. Onshore turbines are governed by strict land use and zoning laws. The zoning map of Germany, for instance, illustrates how turbines are strategically placed to avoid ecological zones and minimize public inconvenience. Offshore turbines, on the other hand, are subject to complex maritime laws as the, the multiple stakeholders involved from environmental agencies to government authorities. The EU Marine Strategies Framework Directive reference in the visual exemplifies efforts to balance energy development with marine protection. These regulations are critical for ensuring the sustainable growth of wind energy. Let's discuss about some case studies. Highwind Scotland. The floating turbines showcases the world's first floating wind farm. Located 25 km offshore, it has capacity of 30 megawatt and achieved a remarkable 56% capacity factor in the first year. The accompanying performance graph emphasizes how this capacity factor far exceeds typical onshore average of 30 to 40. Roscoe Wind Complex, Texas. This wind farm highlights its immense scale with a capacity exceeding 780 megawatt. The case study also demonstrates effective community engagement and adherence to environmental regulation as depicted in community feedback visuals. The slide categorizes turbines by location, size, and axis orientation. The size comparison clearly show how offshore turbines dominate the large size category, while onshore turbines are more commonly medium sized. The diagram comparing HAWTS and VAWTS highlights the dominance horizontal axis wind turbines due to their scalability and efficiency. Vertical axis turbines, though less common, are gaining attention for urban environments. As seen in the urban deployment image, these classifications demonstrate the adaptability of wind turbines to diverse settings. Let's examine the comparing capacity factors and cost. Offshore turbines achieve capacity factors exceeding 50%. The efficiency stems from consistent wind speed and the ability to deploy larger turbines. Onshore turbines with capacity factor of 30 to 40% exhibit greater variability due to terrain and obstacles. Challenges in development. Let's discuss the challenges. Onshore challenges include limited land availability, public opposition due to noise and visual impact. Offshore challenges include high cost of installation and maintenance, corrosion and grid connectivity issues due to underwater cables and substations. Addressing these challenges requires continued innovation and policy support. Let's discuss about the wind speed and power density. This slide provides detailed comparison of wind speed and power density. The wind speed graph shows offshore wind speeds peaking at 9.7 meters per second at 80 meter height, significantly higher than the 7.8 meters per second for onshore system. This difference is attributed to the lack of obstructions over open water as illustrated in the terrain comparison graphic. The power density chart emphasizes offshore advantages with values reaching 435 watt per meter square at 70 meter compared to 360 watt per meter square for onshore locations. This matrix underlines the superior energy potential of offshore turbines. Offshore and onshore voltage comparison. Let's analyze the voltage comparison chart. The offshore turbine operates at a higher voltage compared to onshore system, a direct result of larger turbine sizes and stronger, more consistent wind speed. Higher voltage in offshore system enable effecting long distance transmission and reducing energy losses when supplying electricity to coastal urban centers. In contrast, onshore systems with their moderate wind speed and smaller turbines operate at lower voltage, suitable for shorter transmission distance in rural and suburban areas. Offshore and onshore current comparison. The current comparison chart reveals another layer of insight. Offshore turbines generate higher current values, particularly under optimal conditions, due to their ability to operate closer to rated capacity. This is supported by the consistent wind profile over open waters, as seen in the earlier wind speed graph. Onshore turbines, while efficient in ideal locations, produce lower current outputs on average, reflecting their dependence on variable wind speed and terrain influences. Now consider the power comparison chart. Offshore turbines clearly outperform onshore systems, delivering higher power outputs consistently. This is direct result of higher wind speed, averaging 9.7 meters per second offshore versus 8.2 meters per second onshore. Larger rotor diameters capturing more wind energy. The exceptional relationship between wind speed and power output is evident here. Offshore turbines benefit significantly from even slight increases in wind speed, translating into much higher power generation. For example, at optimal pitch angle of 35.5 degrees, offshore turbines harness wind more effectively, achieving greater power output compared to their onshore counterparts at the same pitch angle. Looking at the current and power data together, we can infer offshore turbines provide a more stable and scalable energy source, ideal for large-scale energy demands in the urban coastal region. Onshore turbines are more suitable for localized power generation, especially in areas where the land availability and lower cost are critical factors. The data underscores the trade-off between efficiency, scalability, and cost in deploying wind energy systems. In conclusion, offshore wind turbines with higher voltage, current, and power outputs are ideal for regions with limited land and high energy demands despite their higher cost and maintenance challenges. Onshore turbines offer a more economical solution for areas with accessible land, moderate wind resource, and smaller energy needs. Both systems are integral to global energy transition, with their deployment determined by geographic, economic, and environmental factors.